Hello everyone. Um, Welcome to the week 3 problem solving session on Introduction to Algorithms and Analysis. So this week mostly was a discussion on the comparison sorts and partition sorts, their analysis, specifically quick sort, randomized quick sort, and then professor discussed about heaps. How do we form a heap? How do we perform some operations on the heap? And then how do we use heaps and the heapify operations, max or min heapify, that we discussed to sort the array. Right, so that was heap sort. So what I'll do right now is I will give a quick overview of quick sort and heap sort, and then we can take some problems on both of these, right? So let us start with quick sort. So the pseudocode for quick sort is, so basically we quick sort an array with given indices p and q, right? So the first step is if, oh, sorry, p and r are the indices, and if p is less than r, then we get a q, basically another element from the array using the partition algorithm that again was discussed last week, right? We partition it, and then q becomes our pivot element, and then what we do is we recursively call quicksort on the two partitions that have formed. So we have an array A, and then starting from P and R, like initially it was like the first and the last element, and then in this element, using the partition algorithm, we found an element Q, and then from P to Q, we perform quicksort again recursively, and from Q plus 1 to R, we perform quicksort on this same next subarray, Q plus 1 to R, right? And of course, the on the first call, our P is 1 and R is n. So of course, yeah, for the first one, the entire array is sent into the function, right? And I won't go through the complete analysis here. I will just state what was already mentioned in the lectures. So the time complexity, right, of quicksort. Okay, so worst case time complexity for quicksort is n squared, right? And this happens when either input is sorted or reverse sorted, right? Or we have partitioned around, right, minimum or maximum element, right? Or like one side of the partition has no element, and that is always the case. Like that keeps happening, right? And that will happen if these two conditions are met, right? So in that case, the worst case time complexity of quicksort is n squared, right? In the best case is best case is n log n, right? So this happens when uh, like we have perfectly half partitioning, right? So yeah, it's like 50-50 partitioning. So the recursion is basically the recursion step, right? For time complexity return is written like this, right? So this A and B are 2 and 2, so it becomes 1, right? So, and using Master's theorem, we can prove that the time complexity will be n log n, right? We can intuitively also see that if the partitioning is always half, then we will end up performing O of n operations on all the partitions, and making the partitions, or basically the number of partitions, will be approximately log of n, right? Because uh, we'll be equally partitioning the tree, and the tree will basically be will end up as O of n log n, of a log, basically of height log n. So these are the like worst and best case scenarios that were discussed. And the variation that was discussed to avoid this worst case scenario was randomized quicksort. And the idea was primarily that we partition around a random element. Okay, so we do not use the partitioning algorithm that was discussed earlier, the partitioning subroutine. Okay, and we just choose the partition randomly. Okay, and because these worst case scenarios are statistically less likely than the best case or the average case scenarios, we can be sure that randomized quicksort will never or like, is very unlikely to hit or to encounter the worst case scenario, and will mostly it will uh, churn out the best case or the average case time complexities, right? So I think there was also a discussion on that quicksort is almost twice as fast as merge sort, so that is also one of the advantages. Uh, but again, like the time complexities are the same, right? The theoretical time complexities. This is same as merge sort, right? But in practice, quicksort is like approximately 2 times fast than merge sort. Okay, now let's quickly discuss heap and heap sort as well, because to understand heap sort, we need to first just understand what a heap is and how heaps are used for sorting. Okay, so the heap is basically a visualization of array as a binary tree, right? So there is no binary tree like that we are constructing in reality. There are no pointers, but we are just visualizing the array and then we are arranging the array in a certain way that follow the properties of the heap that we desire. And one of those properties is max, or you know, analogously min heap property, right? And what is this property? The key, or you can say the value at the node is greater than the value at its children nodes, right? So if we have a binary graph constructed, let's say like this, then any node of this entire heap, basically, if any node has a value less than the value of its children, right? So if let's say this node has value less than any of its children, then it violates the max heap property, right? So basically, in this entire heap, right? So if I were to draw it properly, at every level in this in this tree, in this binary tree, and it's just visualization of the array, right? So the value here, let's say this is A1, A2, A3, blah blah blah. So this A1 should be greater than A2 and A3, and A2 should in turn be greater than what are the values are here, right? So for example, let's say I keep 10 here, right? And then 9 and 8, and then 7, 6, 5, 4, 3, 2, 1, 2, 3, right? So even if the values are repeating, uh, all the nodes have a value greater than their children nodes, right? So this one follows a max heap property, right? So how do we see, right? So if we are given an array, right? Let's say if we have an array A, right, and it goes A1, A2, AI, AN, right? How do we convert this to a tree, right? Or how do we interpret it as a tree? Okay, so the first element of the array becomes root of the tree, right? So this is, we are just constructing a tree from a given array, right? We are just constructing a tree from a heap, but we are currently not enforcing that it follows the max or min heap property or not. Okay. And then for every subsequent element starting from the first element, right? So the parent of ith node is at I over 2th location, right? And the left child of ith node is at 2th location, and the right child of ith node is at 2i plus 1th location, right? So given an array like this, we can analogously construct a binary tree using these rules for indexing. Right now, after converting a tree, we check if it follows the max or min heap property or not. Right, and that is basically how we come up with the heap sort algorithm. Right, so let's take an example here. Right, so let's see if let's draw the heap or the tree, right? The binary tree for this array. 2, 4, 7, 10, 9, 8, 6, 5. Right? So this will be the root element. This will be 2, and there will be 4 and 7, right? Because this will be like I equal to 1, so 2 times I is the second, and 2i plus 1 is third. And for fourth, it will be 10 and 9. And then for 7, it will be 8 and 6. And then we come to 10. For 10, it will be 5, right? Because 10 is at location 4. So 2 times 4 is 8. And we only have 8 elements. Right? So this is currently the binary tree, right? But does this follow? Right? So basically, this does not follow the max heap 5 property. So the question is max heapify A, right? So how do we do that, right? So for max heapify, um, so yeah, we start at our first element, right? 2, and then we check the child, right? And whichever child is bigger, we swap the parent with the child, right? So this is basically the idea of max heapify for the entire uh, in its entirety. Okay, so we replace a of 1 with a of 3, right? So array will become like this. 8, 6. And its equivalent tree will be like this. And then we come to the next element, 4. Right, so 4 again does not follow the maxify property. So we swap 4 with the biggest child between the two, that is 10. Right, so we replace a of 2 with a of 4. Right, so after this replacement, a is 2, 4, 8, 6. So the tree for this will now be like this. And I think we forgot one of the steps here, and that is once we have swapped 7 and 2, what we do is when we do have to indeed swap a parent with its child in the tree, we max CPify the child subtree where the swap was performed, right? So this performing, if we just perform it all on this graph, then 7 will go above and it will become 2. Then this 2 will be swapped with this 8, right? So yeah, this will be 8 here, 2 here. Then we will come to 4. Then we will get 4 here, 10 here, and then we start here. So 5 here, 4 here. And then let's first write the pseudocode for max EP5, right? So first we take the left child of index I, R is the index of the right child of I, and then if L is less than equal to heap size, of A and the A of L, like the value at L is greater than value at I. Right? So basically this violates the max AP5 property. Then we define largest as L, else we keep largest as I, right? And then we check for the right child. And A of R is greater than A of largest. Then largest is R, else like I is already largest, or whatever I and L, whichever is largest. Right. So now we check if largest is not I, then we exchange A of I and A of largest, and then at the end we perform max heapify on A at subtree starting at this index largest, right? So considering our original array, so we start with the first array, the first element, right? And what we actually do is we start from the half. Basically, we start from the level n minus 1 of the heap, right? So if we start from here and then we go down, right? That is how we like build the max heap, basically. So yeah, continuing what we were doing, we start at 10 and then we check at 10, it's balanced. Then we check it 7, right? So 7 is not balanced, so we swap 8 and 7, right? So it becomes 2, 4, 10, 9, 5, right? So we go 8, we go 7 here, 6, and at the location of the last largest that was found, like again, there is nothing to be done because there are no children, right? So we are not going to heapify this subtree, right? So this here we are done. The next one is 4, right? So at index 2, right? So at index 2, of course, it is not following the property. So we swap this. So what we get is 2, 10, 8, 7, 6, 4, no, 5. And at the location of the last maximum, we again check, right? Perform max swapify. So it is also unbalanced. So we swap these two as well. So we are left with this 5 and 4. And again, this 4 now it is at leaf, so we can't go any further, right? And then we come to 2, right? So for 2, we exchange it with 10. And then at the location of 10, we again perform max heapify. So we replace it with 9. So we get 9 here and 2 here. And at 2, like it is already at the root level, so there is nothing to be done for it. So now, right, this is max heapified form of array, right? That this follows the max heap property. And if we were to show it in the array form, right? So it would look something like this: 8, 5, 2, 7, 6, 4. Right? So this is the max heapified um, form of this array. Okay, and how do we leverage this in heap sort? We basically keep switching the uh, what should like because we know the max heapified tree will always have the largest element at the top. We keep switching the element at the top, basically the largest element, with the lowest leaf, right? And then we keep pushing it out of the array. So again, let's take our own example. Okay, so the max heapified form of this array was 8, 5, 2, 6, 4. And this was the max heapified form. Now we want to sort it, right? So What's the algorithm? First of all, we have to form an max heap that we have already done. Then we find the maximum element, and that will always be the first element because this is a max heap, right? And then what we do is we swap maximum with the last one, right? Always. So after the first one, it will be 498527610, and then we push 10 out of the heap, right? So 10 is now no longer part of the heap. Our heap size has reduced by 1, right? So if I draw the tree now, 9, 8, 5, 2, 7, 6. So this tree now, like 10 is out of the array now, right? That is basically the largest value of the whole array, right, that we have separated out. Now to perform this step again, we need to get this into the max heap form, right? Max heap form is required. So we perform max heapification again on this tree, right? And how do we do that? So like if we start at the second level, there is no violation, right? So we go above 4, right? So 4 will be replaced by 9, right? And in this place, we perform it again. So it will be replaced by 5, and now it's all good, right? So now what will we do? Right, so now the max CP5 is 95842. 4276. Okay. Now since this is the max CP5, we replace 9 with the last element, and then we push 9 out. 584279, and then we push 9 out. So the tree now is 6584227. Right, so starting at the second level, all the subtrees are balanced. Starting at root, going like back from here. This will be replaced by 8, right? And this will be replaced by 7. Okay. So the mark CP5 form for this 857426. Again, we replace 8 with the last element, and then we push it out. We push it out. 6, 5, 7, 4, 2. Right. So again, in this, in second level there were no changes, and here it will be switched like this. So it will become 75642. We swap the first element with the last. It becomes 2564, and then we push it out, right? So till now what we have gotten is we got 10, we got 9, we also got 8. Right now we also got 7. Right, so resulting tree 5, 6, 4. So this level balanced 2 replaced with 6. Um, Now it is fine. Right? Now it is max heapified. So 6, 5, 2, 4. Again replace 4, 5, 2, 6. So we get 6 outside the heap. Then we have it's right here 4, 5, 2. So at this level, it is indeed unbalanced. So we get 5 here, we get 4 here, right? It becomes 5, 4, 2, right? Replace these two, 2, 4, 5. We get rid of 5, and then we do the same thing for these two, right? Because this is unbalanced, so this becomes 4, this 2, and then we replace 4 with 2, and then we kick 4 out. So yeah, finally we are just left with this like reverse version of the sorted array. 4, 2. So this is basically the heap sort that was discussed this uh, this week. And let me just quickly take one more question. Machine needs a minimum of 200 seconds to sort 1000 elements by quicksort. So the minimum time needed to sort 200 elements will be what? Right. So for 1000 elements, okay, so time is 200 seconds. And since this is a minimum time, it means it is the best case time complexity, right? So we know that uh, for the best case, it is n log n, right? So let's say this is C1 times 1000 times log of 1000, right? So this was equal to 200, and we want for 200 elements what will be the time, right? So let's say this was T1, this is T2. we can just divide these two. Right, so will be 1000 times. So this comes out to be exactly like approximately 30.68 seconds. Right. So uh, basically what we did was we knew that the minimum time order of the algorithm was n log n, and we were asked about minimum time, like the best case scenario. So we assumed the form of the uh, function based on the order of the time complexity, and then we just put in the values of what we were given 1000 and what we were asked about 200, and this was equal to the time because this was the equation for time, like this time complexity. Right? Then we just divided it, did the arithmetic, and what we got finally was 30.68 seconds. So I think this is more or less what you need for this week's assignment, and I think I will stop the recording here. Yeah, thank you.